Good morning, everyone. So we were talking about feeding channels, and we'll try to wrap up the discussion on feeding channels in today's class. Uh, so in the last class, we were mostly talking about point-to-point channels, both slow feeding and fast feeding channels. We saw that for a slow fading, for a fast fading channel, we have a bunch of approaches. We know that if we have channel state information at only the receiver, then there is of course the standard notion of capacity, which is sometimes called the ergodic capacity, and the ergodic capacity of the fast fading channel with channel state information only at the receiver is given by this expression. It is the expectation over g of half log of 1 plus g square p over sigma z square. So you fix a rate r, and then which is slightly below the capacity, then you can there exist code books for which the probability of error is vanishing with n, as long as r is strictly less than this particular quantity. And this r is fixed beforehand, even before you know what, even before the decoder or the encoder. Anyway, the encoder doesn't know anything, but even before the decoder knows what the channel coefficients are. But if the channel coefficients are known at the transmitter, then you can do power control, and the capacity is a slightly different expression. It's obtained by solving this particular optimization problem. So depending on the channel coefficient, you can vary the amount of power you use in each channel use. Okay, and the optimal power control scheme is basically a water filling scheme over time instead of over space, as unlike parallel Gaussian channels. Okay, but on the other hand, we saw that for slow fading channels, there is no notion of the standard notion of capacity doesn't hold anymore, because no matter what rate you fix in the beginning, there is always a probability of an outage. That is the probability that the channel coefficient is too small for you to sustain a vanishingly small probability of error. Right, so there are different approaches that one can use for slow fading channels. One is, of course, the compound channel approach, where you try to code for the worst possible G. This may work for certain kinds of channels, but in most cases it doesn't. So the compound channel approach gives you zero capacity. But what is more commonly used out there in practice is the so-called outage approach. You say that you can tolerate a certain probability of failure. So with probability P out, which we call the outage probability, you're not going to be able to recover the true message. But if there is no outage, that is, if the channel coefficient is large enough, then you can have vanishingly small probability of error. So with probability 1 minus p out, you will be able to successfully decode the message, and the message is consists of a sequence of bits which is at rate half log 1 plus g square p over sigma square for a suitably chosen g, so that the probability of outage is p out. All right, so this is another approach, and then we also saw a different approach, which I call the broadcast channel approach, which is similar to the outage probability approach, maybe a generalization of the outage probability approach, wherein you now demand that it's okay if not all of the bits go through, but you want to make sure that even if the channel coefficient is a little bit smaller, then you want to get some information through, right? So you can decide a number of thresholds, G1, G2, G3, and how many other thresholds you want, depending on how you can design your system, such that if the channel coefficient is smaller, is less than the smallest gi, then no information goes through. If it is between, say, G3 and G2, then you get some information through. If it's between G2 and G1, then you get more information through. And if it is greater than G1, then you get the maximum amount of information. Right? And the coding technique is basically just superposition codes. And this idea comes from the concepts used in broadcast channels, degraded broadcast channels, wherein you essentially decompose the channel into a number of uh, broadcast channels, degraded broadcast channels, the best channel, a worst channel, and the worst channel. So if the channel coefficient is at least G3, then you know that you're going to be able to recover some amount of information. You'll be able to decode the cloud center of the superposition code. But if the channel coefficient is slightly larger than is greater than or equal to G2, then you know that the effective channel to the receiver is at least as good as this one, so you can decode some more information. And if the channel coefficient is greater than G1, then you know that you can essentially decode all of the information, including the cloud center, the satellite, and all of the satellite code words. All right, so these are various approaches used when you have only channel state information at the receiver. And these are, of course, slow fading channels. Right, so if you have channel state information at both the transmitter and the receiver, then you can do something slightly better because now the transmitter knows what the channel coefficient is. Right? And if the channel coefficient is known with the transmitter, essentially you can just adapt the amount of power you're using. You can adapt the rate, right? So the simplest approach is to vary your rate depending on the channel coefficient. Right? You know that certainly if both the transmitter and the receiver know that the channel coefficient is G, then you know that you can communicate at a rate close to half log 1 plus G square P over sigma square. Right? But this is not really the ergodic capacity, although the expression is the same as that of the ergodic capacity of a fast fading channel. Since this is a slow fading channel, it is not an ergodic capacity because this is only an average rate. Right? So on average, you'll be able to pump in this much of information per channel use. But this really depends on, sorry, there's an expectation over here. But this really depends on what the exact channel coefficient is, right? So, sorry, I should, yeah. So we call C tilde, which is the average capacity or the average rate, and that is the expectation overall G of half log 1 plus G square P over sigma square. All right. And this is an adaptive approach where you change the rate depending on the channel coefficient. Okay. Any questions so far? Okay. So if you know what the channel coefficient is, then sometimes you can do something even better. So note that in most cases you are transmitting, let's say, you're transmitting multiple blocks of the message, right? So you transmit multiple blocks, block 1, block 2, block 3, and so on. And each block is transmitted maybe over one coherence interval. So let me call Tc the coherence time. So each of these is a coherence interval. All right, and each consists of let's see, NC whatever channel use. All right, so since you have multiple such blocks, and if you have only an average power constraint, then sometimes you can do better than just this. Right? What you can do is, if there are multiple coherence blocks, then in some coherence intervals you can maybe transmit a little more power. In some coherence intervals you can transmit a little less power. Right? So you can not just achieve R close to whatever expectation over G of half log 1 plus G square P over sigma square, but now you can also play around with the power. assuming that you're coding across multiple coherence intervals, and the power can be fluctuated, and you can change the power uh, across the coherence intervals. Right. So again, all of this really depends on what the exact system, what constraints need to be satisfied in the system design. Uh, but if all you need to satisfy is an average power constraint, then then you can do power control at the transmitter as well. So you choose a power control uh, parameter t of phi of g. So this is the amount of power you will use in one coherence interval if the channel coefficient is g. So this is the amount of power that you will consume if the channel coefficient is g. All right. So now you know that uh, r needs to be, so as long as r is less than the expectation over g, uh, half log 1 plus g square p of g over sigma square, you know that you are going to be able to decode the true message reliably. But note that phi of g should be such that the expectation over g, uh, p of g should be less than or equal to p. After all, so this power constraint has to be satisfied on average, and now you can optimize this over all possible phi, right? So the capacity, or it's not a true capacity, so that's why I'll call this C tilde instead of C. So the average rate that you can achieve turns out to be the maximum over all possible power control functions phi of the expectation over g half log 1 plus g square phi of g divided by sigma square. And as we've seen before, you can solve this using Lagrange multipliers, and what you'll get is basically a water filling kind of solution. All right. Yeah, so this is again, all of these expressions are almost identical to what we saw in the fast fading channel, but one tiny difference is that in the fast fading channel, you would fix the rate beforehand, so you get some number over here, right? So let's say that this number evaluates to say 1.2. In the case of the fast fading channel, you would fix that the rate is going to be 1.2. Whereas in this case, the rate is not fixed to be 1.2. Depending on what the actual channel coefficient is, g, you will get a different number. But on average, this number is going to be 1.2, right? Whereas in the case of in the case of the fast fading channel, you would say that no, the total number of message bits that I'm going to be able to send is going to be n times 1.2. All right. So all of these ideas, so these are sort of the basic principles, the basic ideas used when you're dealing with fading channels, and for other kinds of fading channels, all of this can just be directly generalized. Right. So the first obvious generalization is for the case where you have either parallel channels or where the channel is a vector Gaussian channel. So for example, the simplest one typical example is a multi-input, multi-output channel. Right. So you have multiple antennas at the transmitter and multiple antennas at the receiver. So far, we had only assumed that the transmitter has a single antenna, the receiver has a single antenna. But now we can assume that the transmitter has T antennas and the receiver has R antennas, and now you can ask if G varies with time. In particular, if G is it's a fast fading channel where in every channel use the channel coefficient matrix varies with time. Then what is the capacity, right? So if you've not seen this before, then basically the channel is given as follows. Uh, so in every channel use, you're not transmitting just a single symbol, but you're transmitting a vector. So in time at time instant I, you're transmitting x1 of I through the first antenna, x2 of I to the second antenna, and so on. So xt of I to the tth antenna, and the receiver has R antenna. So Y1 of I is what is received on the first receive antenna, and similarly YR of I is what is received on the rth receive antenna. And and the relationship between the input and the output is basically just a linear transformation followed by additive white Gaussian noise, right? So Y of I is, so the vector Y of I, or maybe sticking to the notation that we had so far. So YR of I is equal to G of I. So note that G is an R cross T matrix times X T of I plus ZR of I. Right, so this is the simplest model for a fast fading MIMO channel. And now you can ask, what is the capacity of this particular channel? Okay, and of course, so always you want to satisfy a power constraint. So the total, so summation I equal to 1 to n of the norm of x t of I square should be less than or equal to n times p. So you had a power budget initially, even now you have the same power budget, but now you can distribute this power among t different antennas instead of sticking to just one single antenna. Right, and the capacity of this particular channel is known. The capacity is again very similar to what we had for the single antenna case. It turns out to be the maximum overall possible kx, where kx, so you maximize overall possible covariance matrices which satisfy the power constraint. So the trace of kx should be less than or equal to p of half log of the determinant of the identity matrix plus g kx g transpose. All right. So this turns out to be the capacity of a general fast fading MIMO channel. All right, but in the case if the distribution of G is isotropic, that is, it is invariant to orthogonal transformations. So what I mean by invariant to orthogonal transformations is that the density of G is the same as the density of A times G, where for any orthogonal matrix G. So maybe for any ortho normal G. So for any orthonormal G, f of G is equal to f of A times G. So then it is said to be invariant to orthogonal or orthonormal transformations, and G is said to be isotropic. So if GFG is isotropic, then it turns out that you don't have to maximize over all possible covariance matrices, because this maximization this problem is maximized by diagonal matrices, and in fact this turns out to be equal to the maximum over so you just need to maximize over all how much power you're so this essentially you can decompose this into parallel Gaussian channels and this log determinant, this turns out to be IR plus G transpose. The maximizer just turns out to be P over T. So the identity times P over T. So this turns out to be the capacity. Okay. So in the case of the MIMO channel, uh, instead of just there's an expectation here. So in the case of a MIMO channel, the maximizing distribution is again going to be a Gaussian. For a general MIMO channel, it is a Gaussian with covariance matrix Kx, and basically you maximize over all possible covariance matrices. But now if G is isotropic, then the maximizer is simply the diagonal. It's simply an IID Gaussian. Okay, and essentially you can derive this using the same approach that we used for deriving the capacity of the AWGN channel. So there's nothing fancy involved over here. It's fairly straightforward. There are no new ideas over here, but it's good to know that the expression for capacity is given by this quantity. So for a fast fading channel, this turns out to be the ergodic capacity of the channel. Okay, so if you so in case you read any papers on multi-antenna systems, then you will see this expression for the capacity, which is half log determinant of I plus P over T times GG transpose. But note that again, this is the capacity of the fast fading channel. For a slow fading channel, again you either use the outage approach if you have channel state information only at the receiver, or if you have the full channel state information both at the transmitter and the receiver, then this rate is achievable on average. All right, but if you have only at the receiver, then you use the outage approach. So you fix a particular rate if the realization of G is such that half log determinant of I plus P over T GG transpose is larger than the rate at which you're transmitting. Sorry, is less than the rate at which you're transmitting. Then you can't do anything. You will be in outage, but otherwise you will be able to decode reliably. Okay. Any questions so far? So once again, I'm not doing any of these. I'm not proving any of these results. If you really want to prove these, then you should go through the textbook. But the steps are going to be the same as what we had as what we did previously. And in fact, since we derived a very general result for the capacity of any channel, we know that the capacity is the maximum overall possible whatever fx of I of x y, where for any general alphabet x and y. So this is always the capacity of the channel, and of course if you have any sort of power constraint or cost constraint, then you know that the expectation of whatever phi of x, if p is the cost function, should be less than or equal to some parameter. right? So this is the capacity of any memoryless channel, whether it has continuous alphabet or discrete alphabets. And this we know that this is the capacity. Right, so then it's just a matter of simplifying this to get this particular expression. So all that remains is to solve this particular optimization problem. And in general, whenever you have Gaussian channels, the maximizer is almost always going to be a Gaussian. So then you maximize overall possible Gaussians. In this particular case, you maximize overall possible Gaussian vectors, and that corresponds to maximizing with respect to the covariance matrices. All right. So we've already had a good discussion about various point-to-point Gaussian fading channels, and note that all of this holds irrespective of what the distribution of G is. Right? So far we made absolutely no assumption of whether G is whether the channel is a Rayleigh fading channel or as a Ricean channel or Weibull or log normal or whatever. It doesn't matter. All right, so these are very general expressions. For if you have a very specific channel, then it's just a matter of evaluating what this particular quantity is. Right, so if G is Gaussian, then there's a Rayleigh fading channel. If G is Ricean, then it's a Ricean fading channel, and so on. So then it's just a matter of numerically evaluating what that is. But really, these are very general expressions, and you can use them in any fading channel as long as these are whatever fast fading channels or for slow fading channels. Again, we have some characterization of the average achievable rate. All right, so these were for point-to-point channels, but then they can almost easily be extended to multiple access channels as well as broadcast channels, because we've already studied the sort of general theory of multiple access channels and degraded broadcast channels. So it's just a matter of adapting the results for fading channels. If it's a fast fading channel, then we know that this is going to be a memory, then the channel is going to be memoryless. So it's just a matter of evaluating what these mutual informations are. But unlike the point-to-point case, for the multiple access channel and the broadcast channel, we did not get sort of closed form expressions. So the expressions were in terms of auxiliary random variables, but since we have Gaussian channels, many of these auxiliary random variables can just be thrown under the rug. So for a fast fading multiple access channel, where the receiver gets G1 of I x1 of I plus G2 of I x2 of I plus Z of I, where G1 and G2 are random variables, not vectors. The capacity is basically or the achievable rate region, or the capacity region, is just given by this particular quantity. So it's the same as what we had before for the Gaussian MAC, except that instead of half log 1 plus P1 over sigma 1 square, half log 1 plus P2 over sigma 2 square, it's now half log 1 plus G1 square P1 over sigma 1 square, and this is, you have to take the expectation over the respective random variables. Okay, and this is assuming that there is only channel state information at the receiver. All right. So once again, for the specific channel at hand, you can evaluate these quantities. In some cases, it's not very easy to evaluate because these expectations for certain random variables, they may be easy to evaluate, but for other random variables, it might be more complicated. So for example, if G1 and G2 are Gaussian, then this becomes relatively simpler to evaluate, because we know that, for example, G1 square P1 plus G2 square P2 is going to be another Gaussian random variable if G1 and G2 are independent. And basically then it's just a matter of evaluating quantities of the form expectation half log 1 plus G square P over sigma square for Gaussian G. So if you can evaluate quantities of this form for Gaussian G, then you can evaluate all of these three numbers and you get the entire rate region. Correct? So one important point to note over here is that for the Gaussian MAC, for the fading MAC, the achievable rate region is going to be a pentagon, because all of these are numbers and there's no other auxiliary variable. So therefore, this the region described by these three inequalities is going to be a pentagon, and that's a nice feature about Gaussian channels. But note that this is only in the case where you have channel state information at the receiver. All right. Any questions so far? So just 1 second. I'll be back. Seems like someone is at the door. All right. Sorry for the interruption. Yeah. So, any questions? Okay, so this is for a fast fading Gaussian MAC for any general distribution FG1 and FG2, or any FG1, G2. In general, they could also be correlated, doesn't matter. But now, if let's assume that the channel gains are available to the decoder and maybe the encoders as well, right? So now, again, what you can do is you can adapt the power depending on what the channel gains are, right? So, but there's also one subtlety involved over here. Are channel gains available to both encoders? Are both channel gains available to both encoders, or does encoder 1 have G1 and encoder 2 have G2? So decoder knows G1 comma G2, right? And the encoder 1 and encoder 2. So what do these two people know? Right? So we can first assume that encoder 1 knows both G1 and G2. Similarly, encoder 2 knows both G1 and G2. Or we could assume that encoder 1 knows only G1 and encoder 2 knows only G2. And in these two cases, the capacity can turn out to be different, because then the optimization that you do is over different parameters, right? So the amount of power that user 1 puts in and user 2 puts in, so these could depend either only on G1 and phi 2 could depend only on G2. But if both users know both channel gains, then these could be functions of both G1 and G2. Right? So in this case, the rate region is it turns out to be, again, it's a more complicated optimization problem. So you look at all possible power control schemes, phi1 of G1 G2, phi2 of G1 G2, where P1 depends where both P1 and P2 depend on both G1 and G2. You want these to satisfy the respective power constraints. So the expectation of each of these Phi's is less than or equal to Pi. And the rate expression is essentially similar, right? So it's expectation half log 1 plus channel coefficient square times the power divided by sigma square. Okay? So unlike the previous case, where you had only channel state information at the receiver, the achievable rate region now need not be a pentagon. It could be something much more complicated. It's going to be a convex set, but uh, but there's no reason for it to be a pentagon, right? So in general, it's going to be something like this, right? It's going to be some convex set. Okay, and now we don't even have a closed form expression. We don't even have a simple expression for the achievable rate region, because now you need to look at all possible power control functions phi1 and phi2. Okay, but for specific channels, you can try to numerically evaluate these. We can do something similar to what we did in the class when we talked about general multiple access channels. Try to evaluate these rate regions uh, for uh, for G1 and, for a given density, joint density for G1 and G2. Right, and similarly, if you assume that encoder 1, so now the decoder has both G1 and G2. Encoder 1 has only G1 and encoder 2 has only G2. Then now you can no longer optimize phi1 and phi2. So phi1 and phi2 are not functions of both G1 and G2. Phi1 is a function of only G1. Phi2 is a function of only G2. And the expressions are essentially similar to what we had previously. All right, so these are just expectation of half log 1 plus G1 square or Gi square phi I of Gi divided by sigma square. So now we no longer have expressions that we can work out by hand. You'll have to evaluate them numerically. Okay, so very quickly this becomes a complicated problem. But for certain kinds of channels like Gaussian, like Rayleigh fading channels, you can evaluate these numerically. All right. So note that all of these ideas still come from we borrowed ideas from two different things. One was just point-to-point fading channels. The same approaches were used here, and we use standard results of multiple access channels. Okay, so all of these go through as long as the channel is memoryless, right? And you still stick to the standard properties, right? But as soon as the channel has memory, so if it's a frequency selective fading channel, or you have some more complications where the channel is not stationary and ergodic, then things completely change. So you cannot apply these expressions just directly to say that this is the achievable rate region or the capacity of a particular channel. So you have to be careful in what your assumptions are. So what some people do is that even if you have a channel with memory, you somehow try to convert it into a memoryless channel by maybe coding over blocks where each block is sort of independent of each other, and then try to apply the same approach, right? So one common approach used for dealing with uh, frequency selective channels is to use something like OFDM, wherein you try to convert your frequency selective channel into parallel Gaussian channels and apply the results of parallel Gaussian channels over there. Okay, but in general, whenever you're converting a frequency selective channel into let's say parallel Gaussian channels, or even when you're trying to make it memoryless, there is some amount of loss involved because you want to make sure that two blocks are independent of each other. So you try to add in some guard intervals or anything of that sort. There is some loss involved and it is not optimal, but that at least lets you get an achievable scheme, and it lets you get a lower bound on what can be done. Okay, even though it is not optimal, in many cases it is close to optimal, and in any case that is what is done in most practical systems today. All right. Any questions? So these results can I mean almost identically they can be used for degraded broadcast channels as well. Again, there's nothing new over here, but one subtlety is that, so suppose you have a fading broadcast channel. So let's consider the following model where at each time instant I, the transmitter sends x of I, a single symbol x of I, and the receiver 1 gets g1 of I times x of I plus z1 of I. Receiver 2 gets g2 of I times x of I plus z2 of I. Okay, where g1 and g2 follow some particular distribution. Okay. So one difficulty over here is that so we know how to code for degraded channels, right? So if you know that, let's say channel 1 is degraded with respect to channel 2, or channel 2 is degraded with respect to channel 1, then you can design a superposition code. For the better user can decode both the cloud center and the satellite code word, but the worse user, the user with the bad channel, can decode only the cloud center, right? But for that you need to know which user is degraded, right? Because the encoder has to know which message is to be mapped to the cloud center and which message has to be mapped to the satellite code word. Right? But the problem with a general fading broadcast channel is that now you don't know whether user 1 is degraded or user 2 is degraded, because it is possible that with a certain probability g1 is going to be greater than g2, and with some other probability g1 is going to be less than g2. Correct? It's not going to be the case that one is always going to be better than the other. Correct? So in this case, so assume that it's a slow fading channel. So if it's a slow fading channel, if you have channel state information at both the transmitter and the receiver, then you know exactly which channel is degraded, right? And in that case, you can achieve these rates on average, right? So if user 1 is sees a better channel than user 2, then he can decode both the cloud center and the satellite code word, and in the other case, he's going to be able to decode only the cloud center. Okay, so even for the simple fading broadcast channel, if the channel state information is not known at the transmitter, then things become very, very difficult. All right. So again, for the broadcast channel, we don't have a complete solution. For all cases, for all scenarios, we don't have the entire achievable rate region. But for certain special cases, for example, if it is slow fading and you have channel state information at both the transmitter and the receiver, then you can do something. Right? Because we saw that if the channel is not degraded, then we don't know what the capacity of the channel is. Right? Any questions? So this completes essentially what I intended to cover in this particular course. We started off with point-to-point channels, and then I talked about multiple. So after that, we talked about multi-user channels, which was really the focus of this course. And we saw like what is the achievable rate region, what is the capacity region of general discrete memoryless multiple access channels. We got some expressions in terms of maybe these time sharing or auxiliary random variables. And then we looked at broadcast channels, but we saw that even for two user broadcast channels, we could not in general characterize the capacity region. For the degraded broadcast channel, for the two user degraded broadcast channel, we know what the capacity region is. This could be generalized to some extent for these less noisy and more capable broadcast channels, two user of course. But even there, as soon as you go to larger number of users, if the channel is not degraded, then we don't know what the capacity region is. For non-degraded broadcast channels, again, we don't know what the capacity region is in general. And then we applied all of these results to fading channels to sort of study practical wireless communication systems. And for these, again, we saw that for fast fading channels, we can directly apply the techniques we've learned, and we can characterize the so-called ergodic capacity or the ergodic capacity region. But for slow fading channels, there is no notion of ergodic capacity. There's a notion of outage capacity, and you can compute the outage probability and outage capacity, and also the rate regions can be computed. And all of these depend on whether you know the channels, and all of these, the achievable rate region or the best that you can do depends on how much information both the transmitter and the receiver have. So if everyone knows the channels exactly, so if you have channel state information at both the transmitter and the receiver, then that's the best that you can do. And in many cases, we know how to do well. So there already exist coding schemes. If you can somehow, at least for Gaussian channels, if you can somehow reduce the problem into that of coding for the point-to-point AWGN channel, then there are already good coding schemes out there. There are capacity achieving coding schemes, but even for like simple multi-user channels, even two-user discrete multi-user channels, which are not for multiple access channels, we will see that it has been solved somewhat. But even for broadcast channels, for general two-user broadcast channels, designing a good coding scheme which achieves the capacity is still unknown. So all of our but that doesn't mean that a random code can be decoded efficiently. If efficiency is also something which plays a role, then this problem of designing efficient codes for broadcast channels, so that still remains open. So but even characterizing the capacity of broadcast channels still remains an open question. right? So far we only scratched the surface of, maybe not even scratched the surface of network information theory or multi-user channels. There are many topics that we've not been able to cover in this course. Uh, so sort of the next step would have been to talk about interference channels, where you have multiple transmitters and multiple receivers, and this interference among all users. So that is even harder than the broadcast channel. So obviously the capacity is unknown, and and then you can ask questions beyond that. So if you have a general network where it's not just a one-hop communication from transmitter to receiver, but if there are relays in between, or you have a general network where you have multiple transmitters, multiple receivers, and some relays in between, then what is the best that you can do? And all of these, again, still remain open, but many of these tools and techniques can be applied there as well. So the textbook, El Gamal and Kim, is a very useful resource in case you're doing any kind of research in multi-user systems. It's a useful reference to keep in hand, and it sort of tells you what is the best known in the field up to a certain date. I think probably till around 2010 or 2012, it contains the state of the art, but many more improvements have been done later on, which probably the textbook does not cover. And in particular, it doesn't cover how do you actually achieve all of these bonds, right? So that's a topic that we did not cover in this course, which is not covered in the textbook as well. For that, you need to look into error correcting codes, but even those are typically for single user channels and not multi-user channels. All right. Uh, any questions? Any comments? All right, so in that case, we'll stop at this point. So we won't have any more lectures, formal lectures. This is kind of the end of all the lectures that I had planned. But as I mentioned, in the next class, we'll have some maybe some discussions about the papers, so that is in case you have any specific questions, maybe regarding a specific theorem or some steps in the proof of a particular paper, then we can discuss that. So it would be helpful if you already put it up on Piazza, so that I'll know where to look and beforehand, before coming to the lecture, and I can take a look. And then in the sometime next week we'll have the presentations by all of you. We will try to fix a suitable date and time for that. Since there are going to be 6 presentations, so roughly half an hour for each. That's maybe 20 minutes of presentation and a few minutes of Q&A, and we can also have some brief discussions. All right. So again, so if there's nothing else, then yeah, we'll meet next week.
Yes, sir.
Thank you.
All right. Yeah. Thanks. So see you all next week.
Order of presentations?
Sorry, I didn't hear what you said, Girish. Could you please repeat?
Is there any order of presentations, like
Nothing fixed. It's up to you. So I'll maybe just send an order if you have any specific preference. So that's what we'll decide a time. I prefer to do it in 1 or 2 sessions. Maybe not in the regular class hours, because we get just 1 hour. So maybe sometime in the afternoon. So depending on how people are available, we can decide something.
Right. Thank you.
All right. Okay. Yeah. All right. So see you all.